Hey guys, in this video we are going to talk all about acid-base definitions. So I kind of very briefly defined them in the last video over naming acids and bases, but we're going to kind of jump more into that and really talk about those definitions this week. So we have two definitions that we're going to look at, the Arrhenius definition and the Bronsted-Lowry definition. All right, so let's start with the Arrhenius definition. So Svante Arrhenius in 1884 defined them by the product of their dissociations in aqueous solution. So the first thing I want to do is I want to make sure you guys know what dissociation means. So basically, when something dissociates, what we are talking about is that it breaks apart into ions. So when we say it's dissociations in aqueous solutions, we're saying what it breaks apart into when it's put into water. All right, just to put it really simple. So what does it break apart into when it's in water? You may also hear this called ionize. There's another word, and I'm totally blanking on it. So sorry, guys. Ionize, dissociate. Yes. All right. So let's jump into how he defined them. So starting with acids, he says acids are substances that contain hydrogen. All right, so acids have to contain hydrogen. And so when they dissolve in water, they produce hydrogen ions. All right, so when they dissolve in water, they produce hydrogen ions. Now, bases contain hydroxide, and they dissolve in water to produce hydroxide ions. Okay, so most acids do indeed contain hydrogen, all right? But not all bases contain hydroxide. So there are some limitations to this definition because something that is very commonly a base is NH3, which we call ammonia. And ammonia is a basic solution, but it doesn't contain hydroxide. So it wouldn't fit into this definition of acids and bases. So there's definitely some drawbacks to this definition. And then finally, neutral solutions are neither acidic nor basic. They contain salts. And when I say salts, I'm not necessarily just talking about NaCl. I'm talking about any ionic compound. So something made up of a metal and a nonmetal will be a solution that would be neutral. So just a salt dissolved in water should be a neutral solution. Okay, so that's the Arrhenius definition. Super simple, not too complicated. Acids have hydrogen, bases have hydroxide. That's it. That's the definition. Okay. But like we said, that one has some fallbacks and some limitations. So Johannes Bronsted and Thomas Lowry, both in 1923, basically defined acids and bases by the way they react with each other. Okay, so acids are going to be substances that donate a hydrogen. These are also sometimes called proton donors. All right, and then bases are substances that are going to accept a hydrogen. And these are called proton acceptors. So Bronsted-Lowry definition of an acid is a substance capable of donating a proton, and a base is a substance capable of accepting a proton. So we're going to look at this right here. Okay, so first things first that I always do when I am looking at these and trying to identify where my acid and where my base is the best thing to do is to partner them up. Okay, and how we're going to partner them up is basically we're going to pick a reactant and a product, and you're going to partner them up based on which ones look the most similar. So in this case, HF, okay, well, what looks the most similar to it on the other side would be F-1. All right, and the reason I picked that one instead of the other one is because I'm thinking about my definitions of acids and bases, and I know that my acid is going to donate or get rid of a hydrogen. All right, so I know that if that's my acid, on the other side, it's going to have one less hydrogen, which lo and behold is what it looks like over there. All right, we'll come back to that in a second. And then I'll partner up my other ones. So water and H3O plus. They look really similar as well. All right, so based on my partnerships here and seeing what happened to my reactants as they turned into products, I can see that this hydrofluoric acid, HF, oops, did not mean to zoom in. All right, I can see that this HF donated this hydrogen to water. All right, and since that one is my hydrogen donor, right, it got rid of a hydrogen from one side of the reaction to another, I know that HF is going to be my acid. All right, which leaves H2O as my base. All right, so HF is my acid because it donated a proton. I can tell because on this side it's HF. On the other side, after the reaction is taken place, it's F-1. All right, and so it's lost a hydrogen from one side to the other. Whereas with my H2O, it starts out H2O on one side, and on the other side, it's H3O plus. So that means it has gained a hydrogen. Now, guys, on the other side, those have special terms as well. All right, and they are actually called conjugate acid and conjugate base. And I want to quickly define them for you guys, and then we'll actually label them. So basically, conjugate acid-base pair consists of two substances related to each other by the donating or accepting of a single hydrogen ion. All right, so in my reaction up here now that we just looked at, all right, I'm going to have a conjugate acid and a conjugate base. All right, my conjugate acid is always just going to have one more hydrogen than the base. So if water is my base, what it's partnered with on the other side is going to be the conjugate acid. And then if hydrofluoric acid is my acid, then on the other side, fluorine is going to be my conjugate base. So in your partnerships, your acid will always be partnered with your base with your conjugate base on the other side, and your base will always be partnered with your conjugate acid. Now, guys, your acid should have one more hydrogen than your conjugate base, and your base should have one less hydrogen than your conjugate acid. We'll actually write that down in just a second. Okay, so let's go ahead and look at the next one. So first things first, I'm going to partner them up based on who looks similar on either side. Right, so I have NH3. I'm going to partner it with this NH4 plus 1. Again, I'm just looking for a partnership where there's just a difference of a hydrogen from one side to the other. And then H2O and OH will be partners. Okay, so looking at this, we see that water has lost a hydrogen from one side to another, whereas NH3, ammonia, has gained a hydrogen. So that means that water is my acid, while NH3 is my base. Okay, so if NH3 is my base, it's partnered with NH4 plus 1 on the other side. So that means NH4 plus 1 is my conjugate acid, because my base will always be partnered with my conjugate acid on the other side. And if water is my acid, then that means hydroxide is going to be my conjugate base. Okay, I'm going to do one more with you guys. I know there's another practice section underneath this as well, but I'm going to leave that for you guys to try and look at the key later. Okay, so let's do this one. Once again, partnering them up. Start by partnering them up. All right, so HCO3, -1. The other side looks most similar to CO3, -2. It's just lost a hydrogen from one side to the other. And then H2O looks most similar to H3O plus. Okay, so I can see in this reaction that my HCO3 -1 has lost its hydrogen. It has donated it to that water. So since that has lost a hydrogen from one side of the reaction to the other, that makes HCO3 -1 my acid and H2O my base, since HCO3 -1 donated that hydrogen and water accepted it. Now, if HCO3 -1 is my acid, what it's partnered with is going to be my conjugate base, because my conjugate base, once again, should always have one less hydrogen than my acid. All right, and then if water is my base, then that means H3O plus is going to be my conjugate acid, because it has one more hydrogen than the base. Okay. So I'm going to write that down for y'all. So an acid will have one more hydrogen than its conjugate base. And so an acid should always have one extra hydrogen than the base, whether it's a conjugate acid and a base or an acid and the conjugate base. But the acid should always have one more hydrogen. Okay. So the next thing I want to talk about is amphoteric. Okay. Now, initially when I see amphoteric, the word that first comes into my mind is amphibian. And an amphibian is something that can live in the water and on land. Has like two places it can live. So an amphoteric substance is actually something that can act as either an acid or a base. So an amphoteric substance can act as either an acid or a base. And I want to show you guys that water actually does that here. So we can see that in our first reaction, water is acting as a base, but in our second one, water is acting as an acid. So water is an amphoteric substance because it can act as either an acid or a base. All right, so water is probably our biggest example of an amphoteric substance, but there are others out there as well. Okay, so I want you guys to connect the conjugate pairs and do this practice, and then check on the key to see if you are good to go, if you've got it, if you understand it or not, okay? But start with this practice to see how you're doing. Okay, so that's kind of the end of the two definitions, Arrhenius and Bronsted-Lowry. But now I'm going to transition to talk about one other way that we can define acids and bases. And we can define them as strong acids and bases or weak acids and bases. All right. Now, I do want you guys to go ahead and notice that acids and bases can be described as strong or weak, but this is not the same thing as being a concentrated or dilute solution. All right, so the molarity has nothing to do with whether an acid is strong or weak. All right, so we can have a really concentrated, like a highly concentrated weak acid, or a dilute strong acid. All right, so it's not about the molarity at all. Basically, the strength of an acid or base depends on how much it ionizes in water. I'm going to take that out because I like the way that sounds better. So how much it ionizes in water, or how much it breaks apart or dissociates in water. All right, so let's talk about strong acids. All right, so strong acids are going to be highly ionized. All right, and so that means that they're going to almost completely, like almost all of the acid particles are going to break apart. In fact, instead of highly, let's write completely. So is completely ionized. So what that means is that every single acid ion is broken apart. So if I was talking about like, this was my acid before dissociation, all right, after dissociation, every single molecule of acid is going to be broken apart. All right, none of our acid molecules are going to stay together. They're all going to break apart. Typically, strong acids have a pH near like 1. All right, it's going to be a really low pH, and they are good electrolytes. good conductors of electricity. So strong acids are going to conduct really well. We didn't get to show you guys, well, you guys saw it kind of a little bit last semester, but we have those conductivity probes. So if you put it in a strong acid, it would glow really brightly, all right, and it would show really well. So hydrochloric acid is an example of a strong acid. And so whenever we break apart our hydrochloric acid, they all become hydronium ions and chloride ions when they are dissolved in water, and they will be strong electrolytes. And I will define hydronium for you guys actually in the next video. All right, there's 7 strong acids. So hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric are the 7 strong acids, and everything else is weak. You guys do need to know these. All right. You guys remember we gave you a little kind of saying to help you remember this, and it was so, no, clo, brickle, to help you guys remember that those partnered with hydrogen are the strong acids. So hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric acids are all strong. All other acids are considered weak. Okay, so strong acids completely ionize, have a really low pH, close to 1, and are going to be good electrolytes. Conversely, or weak acids are only going to be partially ionized. So again, if this is my acid before it dissolves, after it dissolves, some of them will be broken apart, but most of them are going to stay together in solution and are not going to be broken apart. So you'll have some, but not all. All right, they have a pH of like 4 to 7, all right, and they are going to be weak electrolytes. So that means like it'll still conduct electricity, but if I put my conductivity meter in there, it'll only kind of dimly glow. They don't super conduct electricity, but they do kind of. All right, so acetic acid, like I said, everything else is weak except for those ones. Acetic acid is a really common weak acid. That's vinegar, actually. So it'll break apart just like that. Some of the acetic acid molecules become ions, but most of them stay together as molecules, which is what I drew up there. And just like acids, strong bases completely dissociate, while weak bases only partially dissociate. And they have the same properties, except for a strong base, its pH would be close to like 14, and a weak base would be somewhere in like the 7 to 9 range, with 7 being neutral. All right. The strong bases are the hydroxides of group 1 and 2, except hydrogen, magnesium, and beryllium. All other hydroxides, including ammonium hydroxide, are weak. Okay, so that's kind of the basics of how we define acids and bases. All right, guys, make sure you've done those practice problems that are in right here in the notes and check them with the key to make sure you understand. All right, bye.